Hey, welcome, guys. Yeah, so today I want to talk about the analytic property of the Dirichlet series. Okay, so previously, I think I already introduced the Dirichlet series. So in this video, I want to like briefly talk about some idea of some basic property of the Dirichlet series. And probably this video will be boring because I will prove something. So usually it will be boring, but we can quickly establish some results. And I will give some of the proof. Okay, so this is the Dirichlet series. Okay, so the simple example will be Riemann zeta function if you choose all these fn to be 1. Okay, so we need to study somehow like we want to study the convergence and the property of the Dirichlet series. Okay, so let me just quickly say the results. So first results that I call the absolute convergence. Okay, so basically the idea is that there is for any fn, right? So for any f, there is a convergent, let's say a line which is a convergence, call it abs A B S C I S S A of absolute convergence. Okay, so basically what it says that there is a real number. Okay, so this real number is called sigma A. Okay, so such that for every sigma greater than sigma A, where is I should say, okay, for I should say, okay, so I should say this. So there is a sigma A which is a real number, such that for every s, which real part. So let's say this s is a sigma plus it, such that sigma greater than sigma A, f of s converge absolutely. Okay, so what it means is that for every Dirichlet series, there's a complex plane. You can always find a line. This line is called this point is called sigma A, and at sigma for every point greater than sigma A, it will converge. So this point will converge. Okay. Okay, so this sigma A will be maybe infinity if f of n grows so too fast. Okay, so proof will be very simple. So proof will be if no points on a complex plane such that f of s converge, then we can just choose sigma A to be infinity. Otherwise, let's say we got some sigma A, okay, which belongs to R, such that f of s converge. I should say absolute converge. This is absolute. So idea is that if there is no point on complex numbers such as f of s absolute converge, then we just choose sigma A to be infinity. Otherwise, that we always find some points, let's say converge. Okay, so let's say we find some points, let's call it S, let's call it SA with sigma A plus ITA, such that f of S converge on absolute converging on this SA. Okay, then it's trivial that let's consider now if S greater than, now if we choose S, which is writing sigma plus ID, such that this sigma greater than sigma A, then we can try to bound this term. So we get this. It's bounded by sigma of fn 1 infinity. Okay, so this is bounded by infinity, let's say f of n with this sigma A. Okay, because now S is the sigma greater than sigma A, right? And these guys converge. Okay, so which proves that this guy absolute convergence. Okay. Okay, so this is a very simple proof. Okay. There's another theorem that I want to say. So basically, it's exactly the same as previous. So the idea is that let's say take any Dirichlet series. There's also a thing called I don't know how to pronounce this. Okay, so there's this guy of convergence. okay, which is let's call it sigma, usually called sigma c. So such that this f of s converge on sigma c. Okay, so now there's no absolute convergence. I just say f of s converge on sigma c, which is a real number. Okay, and such that such that the when sigma, let's say I still write s equals sigma plus it, when sigma greater than sigma c, f of s converge. Okay, and when sigma less than sigma c, f of s diverge. Okay, so you can also always find a line such that it has this property. Okay, and obviously you can prove that sigma c, right? Sigma c should be less or equal to sigma a, right? Because once you pass the sigma a, then everything becomes absolute convergence. Okay, so sigma c will less or equal to sigma a, and then larger than sigma a minus 1. Okay, you can also try to prove this. Okay, so proof skip. Okay, because this proof is very difficult. I spend a lot of time if you want to prove this. Okay, so yeah. Okay, and then there's a theorem that I think I also quickly mentioned. It's called Uniqueness theorem of the Dirichlet series. Dirichlet series. Okay, so what this theorem says that let's say f of s is a Dirichlet series, and the g of s is another Dirichlet series. Okay, and both, let's say both converge, both absolute converge when we choose some absolute converge sigma a. Okay, and which is finite. Then you can, and then you know that let's say f of s and g of s are the same. Okay, for every point when for every point greater than sigma a. Okay, then f of n will be g of n for all a. Okay, so this tell you that if you do get to the Dirichlet series and you and the both, right? Let's say both of them will find. Let's say you find some called sigma f, and another is called sigma g. Okay, and then what you also know that if f of s and g of s is the same for large enough sigma. Okay, so let's say, so I think this only need a large enough sigma. Okay, so large enough sigma. If you can find a large enough sigma such that f of s equals to g of s for such enough sigma, then you can prove that f of n equals to g of n for every n. Okay. Yeah, let me just give the proof. I think this proof is not difficult. So let's consider h of n equals to f of n minus g of n. And the h of s will be capital of S minus g of s. Okay, now I know that there exists a sigma 0. Okay, such that h of s converge absolutely on half plane sigma greater or equal to sigma 0, and the h of s is identically 0. Okay, and then we want to show that h of n is 0 for every n. Hopefully this is not difficult. Okay, so we need to prove this by contradiction. Okay, so let's assume that h is non-zero. Okay, so if h is non-zero, then there must be some minimum number n0. So there is a minimum n0 such that h of n0 is non-zero. Okay, so that means you can write h of s into h of n0 n0 s plus, let's say, h1 of s. Okay, so this is the leading term. Okay, so now what we can do is what? Okay, so let's remember this equation. Okay, so now I want to bound this hn0. Okay, so this hn0 is bounded by h1 of sigma. times sigma times n0 sigma. Okay, the reason is this. Okay, the reason is that this h n0 n0s plus h1s is 0. Okay, because h of identically 0. Okay, so when s put to sigma, right? So if you choose s, let's say greater than some sigma 0, then you should get this. Okay, so which means that you can write this. Okay, you can write this, and then it's bounded by the definition of h1 of s is defined to be summation of hn divided by n of s for, let's say, n equals to n0 plus 1 to infinity. So you can plug it. So you get n equals to n0 plus 1 to infinity, h of n bounded at n0 sigma n sigma. Okay, so you can choose sigma to be any kind, right? So let's say choose sigma to be sigma 0 plus lambda, where lambda is large enough. Okay, I think you can see now you get results, right? Because you can bound it. So now n0 sigma divided by n sigma is n0 n lambda n0 sigma 0 n sigma. Okay, because right this and which is less equal to n0 plus 1 lambda, right? Because let's say n is greater than n0, right? At least 1, and there is n0 sigma 0 n sigma. Okay, so let h of n0 is less or equal to n0 sigma 0 n0 n0 plus 1 to lambda. Okay, summation n from n0 plus 1 infinity h of n n sigma 0. Okay, so now you can see, but this guy converge, right? So this guy converge. So this is just some constant. Okay, so which will prove that h of n0 is less or equal to some constant c times n0 divided by n0 plus 1 to the power lambda. So n0 plus 1 to the power lambda. Okay. Okay, so you can so what you try to do, right? Just plug that lambda to be infinity. Okay, then this guy is less than 1, right? So it will become 0, right? So hn 0 is 0. Okay, that's it. Okay. Okay, and okay, and then there's a corollary. Okay, so the corollary. Okay, so corollary is very simple, right? Let's say somebody give you a Dirichlet series. You can consider you can consider f of s, right? You get defined to be g of s. Okay, and this g of s is unique. Okay, unique, and also have the finite epsinica. Okay, so finite epsinica. So basically, I think it's just the corollary of this theorem. Okay, and there is a many interesting identity that you can prove using the Dirichlet, this property of the Dirichlet series. Maybe that's I think okay, so maybe maybe I skip this. I think this is not important. Okay, so I think next time I want to talk about is the Dirichlet series and the symmetry function. So basically, the next thing we were interested is that I want to somehow investigate these two type function, right? So this is the famous one that if you try to bound, for example, if you count primes, that you want to bound somebody give you arithmetic function, and you want to bound this guy, and now it's the logarithmic version. So it's f of x and divided by n. Okay. So we want to connect these two if somebody give you an arithmetic function. Okay. So this is the next topic. Okay, so see you guys next videos.